In image dehazing, existing contrastive learning method introducing the information from non-consensual contrastive samples as a lower bound, which leads the solution space still under-constricted. Moreover, the interpretability of deep dehazing models is underexplored towards the physics of the hazing process. In this paper, we propose a novel curricular contrastive regularization and build a physics-aware dual-branch unit according to the atmospheric scattering model for image dehazing. Here is our overview. The left part illustrates the architecture of a physics-aware dehazing network, which utilizes the physics-aware dual-branch unit, PDU, to extract features. The right part presents the proposed curricular contrastive regularization using consensual negatives, along with a self-contained curriculum learning strategy to deal with the learning difficulty. Contrastive regularization, CR, is proposed to introduce different hazy images as negatives and the ground truth image as the positive, and further uses contrastive learning to guarantee a closed solution space. However, the issue is that the contents of those negatives are distinct from the positive, and their embeddings may be too distant, leaving the solution space still under-constricted. We propose consensual negatives, which can be easily assembled from the hazy input and the corresponding restorations by other existing methods and provide better lower bound constraints. In such cases, the negatives can be closer to the positive than those in the non-consensual space, since the diversity of such negatives is more associated with the haze, or haze residue, rather than any other semantics. Further, due to the different similarities between the embeddings of the clear image and negatives, the learning difficulty of the multiple components is intrinsically imbalanced. As depicted in the figure, during the initial stage, the two types of negatives labeled in the green box are closer to the positive sample compared to the anchor. Consequently, in contrastive learning, they exert a force that pulls the anchor in the opposite direction. However, as the learning progresses, these two types of negatives transition to pushing the anchor in the positive direction within the context of contrastive learning. Therefore, two critical problems arise: 1. How to define the difficulty of different negatives, and 2. How to arrange these negatives according to their difficulty during training. To solve both issues, we incorporate a curriculum learning strategy into contrastive regularization. We define the difficulty of the negatives into 3 levels: easy, hard, and ultra-hard. For easy negative, we use the hazy input consistently. The difficulty levels of the other negatives are dynamically determined during training. Specifically, we measure the average PSNR performance of the network before every epoch begins. In the TTH epoch, a negative is defined as an ultra-hard sample when its PSNR is higher than the network performance, or as a hard negative otherwise. To properly arrange these negatives, we weigh them differently according to their difficulty levels. First, the weight of easy negative is fixed and largest, to ensure that the resultant force is towards the positive such that the anchor is shifted in the desired direction. We give the easy negative a weight that is large enough. In practice, we set this weight to the number of the non-easy negatives, Z. Second, the weight of a non-easy negative SQ at the TTH epoch is defined as equation 1, where IG denotes the hazy input dataset, Q is the index of the non-easy negatives, and gamma is a hyperparameter. Then, our curricular contrastive regularization R** operator is formulated as equation 2. F theta indicates the dehazing network with parameters theta. D I represents the ITH hidden features extracted from the pre-trained VGG19 network. Moving on to the realm of physics-aware deep models, the atmospheric scattering model is commonly used to describe the formation of a hazy image I. It can be mathematically formulated as equation 3. To begin with, we reformulate the physics model to represent the clear image J as equation 4. Then extracting features via kernel K and introduce the matrix vector forms equation 4 can be rewritten as equation 5. Next, we can decompose the matrix KD into a product of two matrices QK, and then, we have equation 6. We can denote A as an approximation of the features Ka that correspond to the atmospheric light and T as an approximation of Q, which is associated with the transmission map. Furthermore, Ki, and Kj can be viewed as the extracted features of a hazy image and its corresponding clear image, respectively. Based on equation 6, we can calculate physics-aware features, J, by equation 7. Based on equation 7, we propose a physics-aware dual branch unit, PDU, regarding the second issue. One branch in is used to produce atmospheric light A. As the atmospheric light is usually assumed to be homogeneous, we use global average pooling to eliminate unnecessary information in the feature space. On the other hand, we cannot apply global average pooling for the approximation of Q due to a loss of information, as the transmission map is non-homogeneous. We choose to extract transmission map T using a sequence of convolutional layers. The PDU approximates the features corresponding to both the atmospheric light and transmission map in dual branches, considering the physical characteristics of both factors. This approach allows for more useful features to be estimated in a dual interactive paradigm. Here is quantitative comparison on the synthetic and real-world datasets. Our method can achieve best performance on both datasets. The proposed curricular contrastive regularization adopts a unique consensual negative-based approach for dehazing and incorporates a self-contained curriculum learning strategy that dynamically calibrates the priority and difficulty levels of the negatives. It is also proven to enhance the performance of SOTAs as a generalized regularization technique, surpassing previous related strategies. To verify the generality of our curricular contrastive regularization, we apply it to different SOTA methods and compare it with several other universal regularizations. The results are summarized in table. Our method achieves significant improvements in PSNR and SSIM on all 5 SOTAs compared to other regularizations, except for a slight decrease of 0.0012 in SSIM compared to consensual CR on GDN. Now we show some visual comparison on synthetic datasets and real-world datasets. Our method generates the most natural restoration that preserves more details and involves fewer color distortions. Thanks for watching.